Hello and welcome back to the Strata Conference. It's Alex Howard from O'Reilly Media here, and we've been talking a lot about big data all day and all week. With me I have Jon Jenkins. If you were tuned in to the stream earlier this week, you actually got to see him talk live about the Kepler mission. And if you are online, you can go to www.nasa.gov/Kepler and learn more about the mission while we talk. So thanks for joining me here.
Well, thank you. It's great to be here.
So 2 years of the Kepler mission now. How much data has been generated roughly from all that time?
Roughly. Well, we generate about 1 gigabyte of data a day, and we bring that data down nominally once a month. So let's see, we launched in March of 2009. I'll let other people do the arithmetic, but it's stacking up every month, yes.
Now that's a pretty large amount of data that's pretty far away from you here on Earth, us here on Earth, right? How much time does it take to transmit, and what kinds of ways is being bounced through the ether?
Well, we bring down all of the data through the Deep Space Network, and we're operating at Ka band. We're the first spacecraft to actually send down data on Ka band, and so proving that ground for NASA for future missions. The bandwidth allows us to bring down 5 megabits per second at this point in time, but we're in a drift-away orbit from the Earth. The spacecraft is trailing the Earth and gets 1 week behind it each year, and so at the end of 4 years we'll be 1/2 of the distance between Earth and the Sun away from the Earth, and as we drift away over time the bandwidth will diminish and we'll be sending back less, we'll have less bandwidth, so we'll be sending back data at a lower bit rate. But right now it's 5 megabits.
Now for people who aren't familiar with the Deep Space Network, can you explain a little bit more? Do we have routers in space?
We do have routers in space. The Deep Space Network is not part of that system. That's TDRS. Deep space probes use the Deep Space Network, and we have 3 locations on Earth that are roughly equally spaced in longitude. So there's a deep space station in Goldstone in California in the Mojave Desert. There's one in Madrid, Spain, and then there's one in Canberra, Australia.
Spread all around the world. So
that's right. That's why, so that you could see any spacecraft at any time from at least one of the stations.
Got it. So the big question, has Kepler given us any more insight into whether life is out there, and if so, what?
Well, Kepler is designed to find Earth-sized planets orbiting sun-like stars. And what we do is we watch for instances when a planet crosses in front of its star, from our point of view, blocking a small fraction of light. And so we're here in New York City, and it's kind of like looking at this building from afar at night with all the shades up, and then one person in one room drawing down this shade by a centimeter or so, because it's a part per 10,000 change in brightness that we're looking for when we're talking about a small planet like the Earth crossing in front of the Sun. Now, that gives us a lot of information about the planet. The interval between transit events, or these crossing events, gives us the orbital period, the time it takes for it to go once around its star. And if you know the mass of the star, which we can estimate from other observations, then Kepler's laws tell you the distance of the planet from the star. And if you know how hot the star is and how big it is, which we do, then that tells you what the equilibrium temperature is for that planet in that orbit. So you can tell whether or not it's in the habitable zone, which is that range of distances from the star for which liquid water could pool on the surface. So that's what we're really interested in, is conducting a cosmic census of the habitable rocky planets in the solar neighborhood, in our part of the galaxy. Now, we can tell whether or not liquid water could exist on the rocky surface, but we can't tell that there's an atmosphere there, and we can't tell what's in the atmosphere. So Kepler, in and of itself, cannot determine whether there's life extant on the planets that we detect. That's a much bigger job left for follow-on missions to Kepler.
Okay. How many planets do we have of interest now, so to speak?
Well, in February of this year, Kepler released 90 days worth of data, bringing the total number of days of data that we released to the public to 120. And when we released that data, we identified over 1,200 candidate planets in that data. Now, we don't call those planets because it takes time to do the follow-up observations to confirm or validate whether or not each of these candidates is actually a planet, because there's a small probability that it could be an eclipsing binary in the background of our target star, for example, that's masquerading as a planetary signature. But we believe that over 80% of our candidates are bona fide planets. And at that time, we'd identified 54 planetary candidates in or near the habitable zone of the stars they were orbiting. So we're making great progress, but there's much more progress that's just around the corner. In fact, today we released quarter 3, which adds another 90 days worth of data to the archive that's available for anyone in the public to go and download. It's the best condition data set that we have now out in front of the public, because we learned through quarter 2, which was the first 90-day segment that we took, that was 90 days long, how to operate the spacecraft and how to make things run smoothly. So quarter 3 data is out there now. It's absolutely fabulous, and we're hoping that people go download it and find some planets in there. In fact, there's a citizen science project called Planet Hunters that's an offshoot of Galaxy Zoo, and this week they just announced that they've identified 2 planetary candidates in the data that we had failed to name as planetary candidates ourselves.
So let's just step back a sec here.
Sure.
You're saying that you released data.
That's right.
Planet Hunters, which is an outgrowth of Galaxy Zoo, which I think galaxyzoo.org. People went in there and found things that you didn't.
Well,
where to put it?
It's a little bit more complicated than that.
As it always is.
So Planet Hunters is this absolutely fabulous site. In fact, some of our science team members are actually part of this consortium, and what they do is they serve our public data to the public and give them tools for which they can observe and actually look at the light curves by eye and note whether there might be transit signatures in those light curves or whether the light curves look like they're irregular, like some kind of variable star. And so they're hoping that people will be able to, through crowdsourcing, identify variable stars and categorize variable stars, as well as identify planetary candidates that, for whatever reason, we missed. Now, in this case, the 2 planetary candidates that they've identified were identified in our pipeline by the transit detection algorithm, but our pipeline doesn't produce candidates. It produces threshold crossing events. So it produces a list of stars that have transit-like features that need to be vetted and elevated to candidate status by people. And so that's where a citizen science project like this can actually make sure that they glean all of the wheat grains that may have fallen off our truck as it trundled by. And it's a great way to engage the public because they are doing a great service and doing real science. So, and they're giving us feedback, so we can go and look at those light curves and understand why we, for whatever reason, failed to identify them as Kepler objects of interest. So there's a lot of synergy between Planet Hunters and the Kepler project.
And for people who want to discover this themselves, what's the website to go to?
PlanetHunters.org.
PlanetHunters.org.
That's right.
That's about as good a place to close things as I could think of in terms of looking at the data, looking at how people relate and why it's important.
Right.
Help you with your mission.
Well, thank you. Yes, we look very much forward to finding the smaller planets, and when you're looking for an Earth-like planet around a Sun-like star, it takes about a year to have at least one transit. We need to have at least 3.5 years of data before we can find Earth-Sun analogs, but the machine is operating beautifully and can continue to do so for at least 10 years. And in fact, next February, we're up for review for an extended mission. So I hope that the excitement of the science and everything that's happening around Kepler and this explosion of exoplanets that's going on will help propel us into an extended mission so that we actually complete the census for Earth-sized planets in the habitable zone of Sun-like stars.
It'll be fascinating to watch that. I'm glad we'll be able to experience that together collectively too now.
Well, buckle your seatbelt because we're discovering planetary systems like nothing anybody has ever imagined.
Well, with that, thank you very much. It's Jon Jenkins of NASA's Kepler mission. You can find that at www.nasa.gov/Kepler.